So welcome back, everybody, for the second day of lectures. So we are very happy to have Juan Maldacena, who's going to tell us about lectures on quantum aspects of black holes. I'm not going to embarrass myself introducing Juan. Everybody knows Juan. But I should say that he has been very kind in accepting this invitation and also accommodating us because it's an awkward time during the day for him. So we are very grateful for that. So over to you, Juan.
Well, hello everybody. I hope everyone is doing well. So the lectures will be on quantum aspects of black holes. And the lecture plan is that the first lecture will be on mostly generalities on the black hole information problem. The second will be mostly about chaos in the near horizon geometry and traversable wormholes. And the third will talk a bit about longer times, so issues that have to do with looking at black holes and how they evolve over long times. Okay, so in this first lecture, we will try to cover quantum aspects of black holes. I'll review a bit some things about black hole thermodynamics. We'll talk about the central assumption or central dogma and certain hypotheses about black holes. And then we'll talk about the aspects, problematic aspects about this hypothesis, which go by the name of the black hole information problem. Then we'll discuss some aspects of simple versus complex observables. We'll discuss a bit about entropy, entangled black holes, and maybe if we have time, we'll start discussing some simple 2D gravity theories. So first, we can say a few words about classical black holes. You probably all have seen this Penrose diagram of a black hole that made from collapse. So we have a very big star that collapses into a black hole. So and we'll use the Penrose diagram. So as you know, the vertical direction is time and the horizontal direction is space, and light rays go at 45 degrees. The interesting aspect about the black hole geometry is that there is a region here, which is the interior, which looks like a collapsing geometry, like a big crunch, that is invisible from the outside. So here an observer sitting outside will receive light rays only from the region of the space-time that is outside the horizon. So the horizon is the set by the light ray that neither makes it out, neither goes into the singularity, sort of is sitting at a fixed radial position in this region. Okay, so that's the geometry of the classical black hole. Is a nice consequence of the Einstein equations. Another interesting consequence of Einstein's equations is that the area of the horizon always increases. That, as we will see, will be related to the second law of thermodynamics once we identify the area of the horizon with the entropy, which I'll review in a second. But here we see in this particular example that the area starts very small here, and then it grows up to the surface of the star, and then it stays constant here. That's the constant area of the horizon in the Schwarzschild geometry. So the Schwarzschild geometry describes only the white region of the Penrose diagram. Here is the Schwarzschild solution. So that's the solution that was written soon after general relativity. It's the simplest spherically symmetric vacuum solution of Einstein's equations. And of course, it has the horizon here is at when r is equal to rs, and the coefficient of the time direction shrinks to 0. That looks like a singularity, but it's just a coordinate singularity. You can go to coordinates where the geometry is not singular. Now, classical black holes were very confusing, and it took a long time to understand the proper geometry of the Schwarzschild solution and what happens when black holes collapse and so on. And as I said, it took about 50 years to understand the classical geometry of the Schwarzschild solution. It was really completely understood only by Kruskal, about 50 years after Schwarzschild. And once we include quantum effects, we will see that black holes are even more confusing. And we haven't understood all those confusions yet. So we now move on to quantum mechanical aspects of black holes. the theory we will consider. So first, let me make a comment about the theory of gravity, in which we are going to compute these quantum mechanical issues with black holes. And this is an approximation to quantum gravity, which is called semi-classical gravity. And it consists of the following procedure. So we start from a classical solution of Einstein's equations, and then we quantize the fields. And if necessary, we resolve Einstein's equations, where we put the expectation value of T mu nu in the right-hand side. And in this way, we can then go to higher orders and systematically improve the approximation. Because the theory is not renormalizable, it means that when we go to higher orders, we'll have to introduce new counterterms. Those are arbitrary constants that we have to define in some way, or measure, or make some hypothesis about their values. But this is an approximation that works order by order in perturbation theory, and it's well defined. So as I said, at any order in perturbation theory, we can have a finite number of parameters that have to do with those counterterms we need to put in. And so that's a well-defined theory. Now, there are some more complete theories, like, for example, string theory. In that case, all these counterterms are fixed, and there are no arbitrary parameters. So that's a better defined theory. But this formalism of semi-classical gravity is a pretty good framework for approximate computations that involve distances much larger than L Planck. And in the black hole context, what that means is that the Schwarzschild radius of the black hole should be much larger than L Planck. Now, this approximation can also be used in inflation to calculate primordial density fluctuations. And this is something that we use to explain the universe we see. Now, the main result that arises by using the simplest approximation of black holes, of quantizing fields in the background of a black hole, is that black holes have a temperature. And the temperature for the Schwarzschild solution has this particular formula. And it sometimes is stated as in terms of the acceleration or surface gravity of the black hole. This is really the surface gravity redshifted to infinity. So the actual surface gravity at the horizon is infinite. So the proper force that an observer sees, that sitting at the fixed radial position, increases to infinity as we approach the horizon. Now, the main reason we see this temperature is related to the fact that an accelerated observer in Minkowski space also sees a temperature. And this is a very important aspect of black holes and very important physical phenomenon for this whole discussion. And Cheng will give a tutorial where he will discuss the derivation of both of these statements in more detail and from various points of view. So I will not discuss them, but just assume them. Now, once you know the temperature and you know the mass of the black hole, you can use, of course, you know the mass just from the general relativity. So you can use this formula to calculate the entropy. And the entropy you get is the area of the horizon in Planck units. Well, of course, here in this formula, we've set a bunch of constants to 1, such as h bar, c, and the Boltzmann constant. And the appearance of all those constants implies that this formula lies at some crossroads between gravity, quantum mechanics, special relativity, of course, general relativity, because we have gravity, and quantum mechanics, and statistical mechanics. Now, some exercises, you could do the following thing. So you could compute the mass and the size of a Schwarzschild black hole, which would look white. So there is Hawking radiation at some temperature. And you could figure out what is the mass and size of a Schwarzschild black hole that would actually look white to our eyes. You could also estimate the life of a black hole using the black hole radiation formula to estimate the energy emitted by the black hole. And you also can estimate the entropy of a solar mass black hole or or a black hole like the one that was imaged by the Event Horizon Telescope that has 1 billion solar masses. And you compare these things with the entropy of all stars in the universe, or the entropy of the CMB in the observable universe. Anyway, so those were some exercises. So now I would like to comment on something, well, some relationship between black holes and the Sitter space. So this is the Penrose diagram of a black hole in anti-de Sitter space. It's very similar to the black hole in flat space, except that instead of having an asymptotic boundary, which looks like here is just the time-like boundary. And here I'm representing the so-called eternal black hole, which is the full Schwarzschild solution, which contains two asymptotic regions, one on the left side and one on the right side. So in some sense, these are two black holes that are sharing a single interior. Now, very important property of the black hole is that an asymptotic time translation symmetry, so what looks like a time translation symmetry far away, near the horizon acts as a boost. And so it's like a boost symmetry around this point. And this is a central feature of a black hole. It's related to the temperature, and as we will see, this fact will play an interesting role in many discussions. Now that feature is also shared by the Sitter space. So the Penrose diagram of the Sitter space can be represented here. The difference is that in the case of the black hole, there is a singularity here in the future. So the universe sort of collapses. This is the other way around in the Sitter. The universe expands forever in the future, and also in the asymptotic past. This is for global de Sitter space. And then these vertical lines represent observers who are sitting at, let's say, the North Pole or the South Pole of the spatial sphere. So the space looks like a three-sphere. So the 3 dimensions of space are compact and form the geometry of a sphere. And this point here represents one point on the sphere, let's say the North Pole, and this is like the South Pole of that 3-dimensional sphere. And on each point on this diagram, there is a 2-dimensional sphere. In any case, in here, an observer who sits at a fixed position also feels like as if he or she is in a time translation invariant situation. So there is a time translation symmetry that looks like ordinary time translation for the observer that sits here. But that same symmetry is a symmetry of the full diagram, of the full space-time, but looks like a boost around this point, okay? Similar to what happens to the black hole. And for that reason, the Sitter space also has a temperature, and it's a temperature which is proportional to the Hubble constant of the Sitter, or the acceleration of the accelerated expansion of the universe. Or you can also write it in terms of 1 over the radius of the Sitter space, radius of curvature of the Sitter. Another thing that is relevant is that in the production of Hawking radiation, or the Sitter radiation, there is a sense in which if you take 2 light rays that are very close to the horizon, these light rays are diverging. So they are moving away from each other. And so in some sense, the universe is expanding in this region. Of course, in the Sitter, it's obvious it's expanding because the whole universe is expanding. But that's also true here. So what that means is that these modes that are emitted as Hawking radiation, if you follow them into the past, these 2 light rays are becoming very close to each other. And that is related to the fact that these modes that look like they have some temperature of order the radius of the space, well, when they are emitted, when you evolve them backwards in time, they are very highly blue shifted, and they correspond to modes which, if you continue evolving them backwards, they look trans-Planckian, so would have more energy than the Planck scale. And this is a feature that sometimes causes some confusions, and we'll discuss it a bit more later. But in both of these cases, we have modes that start out in the vacuum, that naively, formally, they come from infinitely high energies, and they start in the vacuum, and then as the universe expands, they become actual physical particles of long wavelength. Is there a question? No. Okay. Now, this phenomenon, well, the phenomenon of Hawking radiation is not something that has been observed for real black holes, because real black holes are very big, and we saw that the temperature is proportional to 1 over the size of the black hole. So that would be a very, very tiny temperature, smaller than the temperature of the CMB. And for that reason, it's not possible to see for actual black holes. And even in principle, even if we were close to a black hole, it would be very difficult to see. On the other hand, the Sitter temperature is actually quite relevant to us, and I'd like to comment on this. So according to inflationary theory, the universe was close to the Sitter at early times, and it expanded like the Sitter for a time set by a certain clock, the clock of a rolling scalar field. And the temperature can be viewed as fluctuations in this clock, so that in different regions, the universe expanded at different amounts. And this causes some regions to expand more than others, and this causes density fluctuations, which are of order 10 to the -5 that are seen in the CMB. And we think that this is the mechanism that actually produce these fluctuations, and these fluctuations are necessary for the formation of structures like galaxies, stars, planets, and eventually us. So this effect is actually pretty important for the description of our universe in the context of cosmology. Now, this talk will be mostly about the context of black holes, but I just wanted to make the statement that even though Hawking radiation has not been seen for black holes, a similar effect, which is what I just reviewed, is central to our theory of structure formation in cosmology. Now we'll discuss some conceptual questions that were raised by Hawking radiation.
Juan, there is a question in the chat box.
Yes. Yes.
So the question is, are the light rays diverging in the de Sitter case as well, or anti-de Sitter case?
Yes, in both cases, yeah. In both cases, near the horizon, as you go to the future, the light rays are diverging. Yes. So that feature is common to both cases. Okay, so the conceptual reasons, the conceptual puzzles or questions have to do with what happens when the black hole evaporates. And so here we imagine the same figure we had before of the black hole collapsing. That's this figure at early times. But now we'll include the effects of Hawking radiation. So the black hole will emit Hawking radiation, and it will lose mass, and over time it will evaporate completely. Now, we cannot track that process up to the very end by using the semi-classical theory, but we can track that process very close to the end. And we'll assume that at the very end, so when the black hole is very small, the black hole evaporates completely and leaves just the empty space. And if we make that assumption, then the diagram that we expect will have roughly this feature, that we'll have the collapsing geometry, we'll have the final flat space geometry, which is this region here. This vertical line is like the origin of flat space in radial coordinates, and we'll have some radiation that will be the radiation that the black hole emitted. Now, this radiation is in a mixed state because it's entangled with the partners of Hawking radiation, which are modes that are going into the singularity. Okay, and so for that reason, if you form the black hole from a pure state, so imagine that all the quantum fields were in a pure state, even the star was in a pure state, just for the sake of the argument, it collapses, and then because you only can receive information from the region behind that is outside the horizon, you're only seeing a portion of that pure state. And that portion is mixed due to the fact that these Hawking radiation modes have partners which are inside the black hole and are entangled with it. You'll see that the fact that these modes are entangled, you'll see in more detail in Yimin's Chen's tutorial on Hawking radiation. And so that's, so if you just sit outside the black hole, it looks like a pure state would go into a mixed state. Now, even before we get into that, there is actually one other question we can ask about this. That is a more elementary question, which is the fact that the area was increasing in the classical theory, but due to the process of Hawking radiation, the area of the horizon could decrease. So what happens with the second law? I think the resolution to that problem is simply that the total entropy as seen from the outside should be the area of the horizon plus the entropy of matter outside the black hole. And this entropy of matter should include also the entropy of the quantum fields. So the entropy that we have that arises because we can only observe the region outside the horizon for the quantum fields. So that gives an entropy which has a UV divergence, which is cancelled by some renormalization of the Newton constant, as we will see more in a second. Now, once you include the Hawking radiation, it turns out that this whole quantity actually, the entropy actually increases. So the Hawking radiation process makes the entropy of the quantum field theory increase, and it increases more than the area decreases. So actually the whole process is sort of irreversible as a thermodynamic process, and this entropy, which should be viewed as the thermodynamic or Boltzmann entropy of the system, actually increases. Now, these various results have inspired a certain hypothesis, is central to the study of quantum black holes, or for the things that we will be talking about. And this is the idea that the black hole can be viewed as a quantum system. And we're calling this a central dogma, or central hypothesis. Dogma means hypothesis. So a black hole, the hypothesis is the following: that if you look at the black hole from the outside, it can be described as a quantum system with s degrees of freedom, or s qubits, where s is the area over 4. This is just simply a statement about the dimensionality of the Hilbert space, which should be e to the s. And not only that, but it also evolves according to unitary evolution as seen from the outside. So here, important things is that one important thing is that this quantum system describes the black hole has a finite entropy, and a finite entropy of order. The area is not infinitely big, the Hilbert space that we need. So the idea is that we can replace the black hole by some system of qubits, as long as we stay outside the black hole. So in other words, if we include a over 4g Newton mysterious qubits, then we can replace this whole region that is near. So we take the original space-time, we mash in some cutoff surface somewhere away from the black hole, and we replace the whole space-time inside this cutoff surface, even including the black hole, by some system of qubits. The hypothesis itself doesn't tell us what the system is. It only tells us that the system exists and its evolution is unitary. And for the moment, this statement does not say anything about the interior. It's just a statement about the exterior, about how the black hole looks, well, or how the final dynamics of black holes looks like from the point of view of the exterior. And so I should, this hypothesis sort of permeates what the way we sometimes think about black holes, and it makes some words a little confusing. So let me try to explain. So sometimes when we talk about the black hole, we are talking about the object as viewed from the outside. Sometimes we could also mean the full space-time geometry, including the interior region. And and both are good names, but they are talking about slightly different points of view. So we will mostly use the word black hole, and in this context as referring to the black hole as seen from the outside. So then if you assume this, then this assumption is definitely not manifest in general relativity. And in fact, it seems to be problematic. So reasons why this assumption, so what we are going to see now are reasons why this assumption might not be correct. Okay. So one we already saw. So we saw that the outside region could start in a pure state and would evolve to a mixed state. And we would only restore purity by including the interior modes, but those are not visible from the outside. So that's a problem. So there is a way to quantify this problem a little better so that we don't have to wait until the black hole evaporated completely to see a problem. And that has to do with the page curve. And I think Tom Harman will discuss that, so I will not discuss it myself. We could also ask about the black hole S matrix. So if you form a black hole in different ways, how do we actually compute the amplitudes for different states of Hawking radiation to come out? So if the evolution is unitary, how will we compute this? It seems that some of the information goes into the interior and we cannot recover it. There is another form of this information paradox, which involves a black hole in anti-de Sitter space. For example, a black hole does not evaporate. So when the black hole is in anti-de Sitter space, the faraway region of anti-de Sitter space acts as a kind of mirror that the Hawking radiation comes out of the black hole and then goes back into the black hole. So those black holes are not evaporating. But even then, for those black holes, you have an issue because you can excite the black hole and then look at the 1-point function, for example, of some other operator in the excited state, or equivalently, you can look at the 2-point function in the thermal state. And that 2-point function at very separated times should not decay all the way to 0. So we should have some small noise, small quantum fluctuations that, on the other hand, the classical geometry of the black hole would tell you that the 2-point function would decay all the way to 0. But in a finite system, if you perturb a finite system, you should retain some memory of the initial perturbation. And then there is the so-called AMPS paradox, which is really several versions of the AMPS paradox. And it says that if we have an old black hole, its late time radiation should be entangled with the, maybe I'll discuss it in the next transparency. So we start with an old black hole that has evaporated past the page time. So the page time is defined to be the time at which the entropy of radiation would have to be decreasing if the black hole evaporation is unitary. And so this is like more than halfway through the evaporation of the black hole. So in this situation, then the black hole is close to maximally entangled with the radiation. So we mentioned we form a black hole and we emit radiation for a long time, so that the entropy of the radiation is bigger than the entropy of the remaining black hole. And at that time, we think that the black hole will be close to maximally entangled with the radiation. So now the radiation that is emitted after that time should start making the radiation of the entropy decrease. And so that radiation should be entangled with the early radiation. So there should be some entanglement between the radiation that is emitted at late times with the radiation that was emitted at early times, so that together form a state with less entropy than the entropy of just the early time radiation. But in addition, in order to have a smooth near horizon geometry, this mode that is emitted at late times should be entangled with an interior mode, with the mode that with the usual interior mode that usual Hawking emission. The Hawking emission process involves a mode that goes out and a mode that goes in that should be entangled with each other in order to make the space smooth and the quantum state of the fields there, the vacuum. But entanglement in quantum physics is monogamous, so you cannot have like this blue radiation mode that is entangled with two things at the same time. So there is some apparent contradiction. Okay, and we will probably discuss that, how to resolve that. Now, but before we try to resolve all these things, we could wonder why we insist on this central dogma or central hypothesis, given the arguments against it. Okay. So the skeptics would say that, well, we have the black hole that forms and evaporates, and this whole process looks a bit like a universe, which is the original universe, and then there is matter collapsing and Hawking radiation coming out, and this whole process can be viewed as the emission of some other baby universe. So there's some other disconnected region of the universe, which is the black hole interior, which eventually collapses into a singularity. But so they say, well, I mean, in this process, why couldn't the initial state be pure? And then we end up with two universes that are entangled with each other. And so if you only look at one universe, you of course don't get the whole picture. But if you look at both universes, then of course you would see a pure state. And so the only reason you don't see a pure state is because you are making a mistake when you look at just the universe here from the outside. Okay, so that's essentially the argument that the skeptics would make. And it looks like a reasonable argument. So if you think about about gravity as from the point of view of third quantization, so where you would have a theory of many universes, it seems that it's a fairly reasonable argument. Now, on the other hand, there is some evidence in favor of this hypothesis of the so-called central dogma. So the first evidence, I think it's just black hole thermodynamics. So if that picture of the splitting universes was correct, then why should the entropy increase? So when so why couldn't entropy go into the baby universe, and then the outside universe might see the entropy decrease, right? So that's certainly possible when we have evolutions of particles or of systems of various kinds. So entropy could be damped into some system you later don't observe, and that's perfectly fine. But the fact that the black hole thermodynamics works is, I think, some evidence in favor of that hypothesis, and was one of the motivations for making the hypothesis in the first place. Now, more concretely, there were formulas from the 90s that compute black hole microstate counting. So they, for the special case of supersymmetric black holes in string theory, you can actually have some argument that displays the microstates of the black hole after some continuation in the coupling. So a strong coupling, you have a black hole, and then you continue the coupling to weak coupling. And there you can count explicitly the states using weakly coupled strings and D-branes and various objects in string theory. And this formula reproduces not only the area formula, but also corrections to the area formula. And there is a very detailed agreement in certain black holes in string theory. And then, so the ADS CFD conjecture, or also the so-called matrix theory or BFSS matrix theory. So these two things are conjectured equivalences between gravities and simpler systems. And they can be viewed as more precise versions of the central dogma. So they are more precise versions in the sense that they give the actual Hamiltonian. In these particular cases, you have to, you don't give the Hamiltonian near the black hole, but you have to go all the way to the boundary of space, to the asymptotic region, and you give the Hamiltonian that describes the whole universe, in the whole universe. And if it includes a black hole, it would also include the black hole, but you have to retreat all the way to the boundary. And there are various tests of this hypothesis. So there are some precision tests that involve integrability, but all these tests involve small fluctuations around the vacuum and do not probe the details of black holes. So the tests that involve integrability. There are also some tests that use supersymmetry. Again, they do not involve black holes. Tests that involve black holes are tests that calculate the entropy. It's usually calculated something called the Cardiff formula, which involves it's a way to calculate the entropy of 2D CFDs. And there is one case where you can reproduce the entropy by using numerical simulations. That's for the black hole made out of the zero brains, or for the BFSS matrix model. So there are a variety of tests that have been made of this, but I think the tests that have been made are not with the precision that is necessary to answer the questions that involve black holes. So to answer those questions that we raised in the past. In the sense, for example, calculating the black hole S matrix, of course, we could calculate it from the boundary theory, but we don't have an alternative way to calculate it using the bulk. So in other words, if this hypothesis is true, the question is whether we can understand it directly using the roots of gravity in the bulk. Or alternatively, you could ask whether we can recover the interior geometry from the full quantum theory that describes the outside. So there was a hypothesis some time back by Susskind that the interior would be also, you could recover the interior from the outside using something called complementarity. Well, it's just the hypothesis that you can recover the interior. And now there is a more modern proposal, which is called entanglement wedge reconstruction, that I will try to review, which is a more detailed proposal of what aspects of the interior and what portion of the interior you can derive. Actually, it was wrong to say that you could derive the whole interior. Actually, you can typically derive only a portion of the interior, as we will see. And I think a full resolution of the black hole information problem should also tell us what happens with the singularity. What does the singularity really mean? In other words, I would say that the whole reason we study black holes can be summarized as a kind of research proposal. So the research proposal is that first we would understand the quantum aspects of black holes. Then we would understand the singularity as part of these aspects, and we'll extract some lessons for cosmology, and we'll make an experiment, and we'll make an experimentally verifiable prediction in the context of cosmology. I mentioned this cosmology aspect because even for the simplest question of Hawking radiation, it is hard to verify for black holes, but for cosmology, it's actually part of our description of our own universe. So it's more likely that we will perhaps verify some aspects of quantum gravity, other aspects of quantum gravity using cosmology than using black holes.
So Juan, there's a question.
Maybe I'll stop here for questions. Yeah.
So Juan, there's a question in the chat box. I think you kind of addressed it, but I'll read it out. Does this central dogma also say that the black hole interior degrees of freedom are something we can't access from outside?
Yeah, so the central dogma doesn't say anything about the interior. So I phrased it purely as a statement about the exterior. What does say something about that is this statement of entanglement wedge reconstruction, which I will review later. So I will answer more precisely that question later.
Okay, any other questions? If you can raise your hand, that will be the best way. So the way to raise your hand is to go to reactions, and then you'll see the raise hand option. Yeah, I don't see any questions.
Okay, very good. So, but feel free to ask questions, please. I mean,
there is a question by Loga.
Okay.
Hello. So
yeah,
Juan, is there a central dogma for de Sitter? Like, what would be the analog for de Sitter?
Yeah, that's an excellent question. No, there is no generally accepted hypothesis for de Sitter. I can tell you a little bit what was said for de Sitter. Let me see if I can go to the right. Okay, so this was the picture of de Sitter. So there are actually two hypotheses that people have suggested. So one is that if you look at the observer who sits in the, let's say, North Pole, Then there is a quantum mechanical system that describes this observer and any measurement that this observer can make. So this is called sort of the static patch system. And for this observer, there is a horizon here of some area, which is the area of this horizon of this surface. It's of the order of the radius of the zeta, well, times some factors of pi and so on. And that would be the entropy of the quantum system that describes this North Pole observer. So that's some hypothesis. It's a little difficult to understand whether it's well defined or not, because this observer is limited in the measurements that he or she can do. You cannot make arbitrarily precise observations. And also exactly how this system is related to the other system or to systems of various observers is a little unclear. In particular, people have not come up with a suitable system that has at least the approximate symmetries, has the symmetries of the zeta space, at least in an approximate way. So those are some problems with this hypothesis, but it might be correct. I don't know. There is no good argument. And the other hypothesis is to say that here in the future, there will be a conformal field theory in the future that lives just on this boundary that will describe all possible observations you can make here in the future. That it's a field theory defined purely in the future that does not involve the interior, but you could calculate the same things you could calculate by using the interior evolution. So these are two possibilities. Maybe there might be more. I would say that based on recent developments, one perhaps interesting twist might be to think that perhaps in the zeta for this observer, there isn't actually a quantum system, but maybe it's a quantum system with random couplings that you have to maybe make some average over those random couplings to see the full de Sitter space. That's maybe some more something inspired in more recent developments, but we don't really know for de Sitter some very clear hypothesis.
There are three raised hands. Manish, you can go ahead with your question. You can unmute yourself and ask. Manish. Okay.
Hi, can you hear me?
Yes.
So my question is regarding that slide that you showed right now. So you mentioned that this time translation on the boundary is generated by the boost operator, and it's also the boost operator also gives, near the horizon, the time translation is given by the boost operator, and this reflects as a boundary time translation as well. So yes. You mentioned this is related to symmetry. So I don't understand the symmetry bit. So I can understand the time translation symmetry on the boundary, but what is this symmetry near the this point at the center?
Yeah, so there is a symmetry that around this point. So let's imagine the whole picture is two-dimensional, just to make the life simpler. So then you could think about boosts around this point, right? And so it moves time forwards here and time sort of backwards here. That just looks like a boost in Minkowski space. And that's a symmetry of the geometry, of these black hole geometries. It's just the symmetry of the solution, of the, let's say, the Schwarzschild solution or Schwarzschild ADS solution.
I'm sorry, there was a connection issue on my end. Can you repeat, please?
Yes, it's just the symmetry of the solution. So it's just a mathematical property of the solution. And part of the issue is to understand this. So of course, you can check just by doing the coordinate transformation that it is a symmetry. The difficult part is to square this symmetry with this central hypothesis we were talking about. to make it consistent with the central hypothesis. That's part of the
Okay.
issue.
Okay. Thank you.
Yeah.
Gopal, you can ask your question. Gopal Yadav. Okay, he's unable to unmute. So Takato,
I can. Okay.
Yeah, okay, Gopal, yeah, go ahead.
Suppose we have a evaporating black hole, and we are coupling this black hole to bath safety, and where we are collecting the Hawking radiation, right? Then we are measuring this Hawking radiation. Then if we are calculating the phase time of this evaporating black hole, then early time it start increasing with the time, and I want to know what is happening at the phase time such that this entropy starts decreasing after the phase time.
Yeah, so this is supposed to be the space-time, and the entropy of the black hole decreases smoothly until the very end, and naively the entropy of Hawking radiation increases all the way to the end, and that's supposed to be the leading space-time describing this system. I think you will see in Tom Hartman's lectures how to compute the Hawking radiation in a way that you actually see it decreasing, but it's a more sophisticated way of computing the entropy of Hawking radiation. But nothing is supposed to happen to the space-time when you go through the page time.
Okay, thank you.
Takato, can you unmute yourself and ask your question? Sorry, just 1 second. I missed by mistake. I muted you. 1 second.
Okay.
Yeah, try to unmute yourself, Takato, again.
Yes, can you hear me?
Yes. Mm-hmm.
Okay. So how are the Hawking radiation and its partner entangled for observer near horizon? I ask this question because naively thinking the temperature near horizon is infinite. So naively thinking entanglement gets stronger.
Yes. So yeah, so we have this type of picture where we have a mode that is outside the horizon. Okay, let me see. The idea is that the quantum fields in the vacuum can be described by, let's say, local degrees of freedom. So there is, imagine that there is a qubit at each point in space. But the state of the quantum field is not the factorized state of those qubits. These qubits are in an entangled state, okay? And so if you separate the space into two parts, that state, if you look at the state only on one of the parts, one of the portions of the space, it will look mixed. And as you of course, long wavelength modes will contain some entropy, but as you go very, very close to the boundary between the two, you start looking at shorter and shorter wavelength modes, and that those give rise to more and more entropy in the of entanglement. I'm not sure if I'm answering your question. But...
I'm asking the observer dependence of the entanglement between two modes.
So, yeah, why is it observer dependent? Yeah, so no, the entanglement is an objective thing. So it comes from separating the original state into two parts. So I think your question is really why. So why should we separate the state in this particular way? And we separate it this way because an observer who stays outside the black hole can only see a portion of the space-time. So it's related to the fact that an observer who stays outside cannot see this part inside. So this observer is forced to consider only the state outside. This observer cannot talk about these modes, cannot observe them, and therefore only looks at the state outside, and that state is mixed and has some entropy.
Yeah, I understand the point, but for observer near horizon, does entangle the strength?
So if there is if there is an observer that really crosses the horizon, right? That observer would see all those modes in a pure state. We see the vacuum, and yeah. So if that observer decides to make a measurement that only looks at the observer at the modes outside, would also see some entropy. But that observer also has the option of looking at both of them and can check that you have a pure state.
Okay, thank you.
But the observer outside does not have that option.
So a couple of questions in the chat box. One, do you want to take them now, or I can read? Yeah, it's up to you.
Yeah, so one of the questions had to do with the fact that the process is quantum mechanical. So the Hawking radiation will be in a highly quantum state. I think, so this is taken into account in the discussion. So I think that was one of the questions. And
yeah, this is Zheng's question, I think, yeah.
Yeah. And another question is whether the Hawking radiation can contain heavier, higher spin states. Yeah, so that Hawking radiation in principle can contain photons, electrons, strings, whatever particles your theory has, and this doesn't change what the hypothesis is. Okay, very good. So maybe we should continue now. So the first point is that if you look at black holes from the outside, the first observation is that simple observables, such as, for example, the expectation value of a finite number of fields, thermalizes. So those simple observables thermalize in the sense that they're at late times, they approach the values they would have for a black hole in thermal equilibrium. So if you form the black hole from collapse, and you look at the fields outside the black hole, they have a value which is similar to the value you would have in thermal equilibrium. And this is roughly what you would expect for a very entropic system. So the black hole, well, this is what you would expect as long as the black hole degrees of freedom interact significantly with each other. Of course, if the black hole degrees of freedom did not interact with each other, then you wouldn't expect it to thermalize. But if they interact a little bit or somewhat significantly with each other, then you would expect them to thermalize. Now, furthermore, there's been a beautiful connection between black holes and hydrodynamics, which is more clear if you consider black brains, actually. And there is a whole fluid gravity correspondence, etc., many things that have been studied in this direction. And of course, for that, it's also important that black holes thermalize, but not only that, but they really behave like fluids in a very precise sense. In some sense, a black hole is a mesoscopic object in the sense that the information problem involves a system whose entropy is large but finite. And the whole question is to reconcile the laws of thermodynamics with unitary and reversible quantum behavior. So when we talk about the problem of extracting information from Hawking radiation or doing some checks of unitarity, these questions are usually very hard in practice. I mean, they are hard even for relatively simple many-body systems of tens of qubits. And so these experiments require sort of exquisite control. Now, let me show you an example of how we can extract information from Hawking radiation. And we can do so by using even the space-time diagram. So first, we let the black hole evaporate completely. So we have the black hole evaporated completely. And we imagine we have the black hole collapse, and we send in some unknown qubits, so some qubit that someone else sent. And our task is to get this radiation and find out what this qubit was. Okay. So what we can do is we can collect all this radiation and then evolve or simulate the evolution backwards in time. And if we evolve backwards in time, we think that we'll go to earlier times, and then eventually this information comes out when we're evolving backwards in time. Now, some of you might say, well, you are cheating. You might think I'm cheating because evolving backwards in time is something very unrealistic. And it's true, it's very unrealistic for an actual black hole that we have. But certainly if we imagine we have control over a quantum system, complete control over a quantum system, doing evolution backwards in time is actually something we can do, and it's a legal operation. And maybe it's, in this particular case, is one possible operation we can do to extract information out of the black hole. And we can't expect to do something simpler than that somehow. So even evolving backwards in time is some relatively simple operation. If the evolution, let's say, forwards in time is simple, the evolution backwards in time should be equally simple. Of course, in nature, there is some universe we live in which is evolving forwards in time, and it's hard to make the black hole evolve backwards in time, right? So that would require very complicated, sophisticated machinery. But this is the type of control that is necessary to extract the Hawking radiation, extract the information from Hawking radiation. Now this process, okay, we said what it was, and it looks simple, but it's quite tricky, because suppose that the black hole evaporates completely, and we start evolving it backwards, but we miss one mode. So for one particular mode, we miss that particular one, and so when we evolve it backwards in time, it will not be in the state that it was supposed to be, that it was when it was evolved forward in time. It will be changed, right? Because it will be changed, when we evolve it backwards in time, this change will be highly blue shifted here as we go back. And it will be a highly blue shifted shock wave that will collide with the matter that was falling into the black hole, and will produce a horizon and a singularity here in the past as we evolve backwards in time. And so we will not be able to extract the information that our friend sent, okay? So, so you see, this is something quite sensitive. So you cannot do it as easily if you make this little mistake, okay? However, according to quantum information theory, it should still be possible to recover the information. So there should be some other procedure you can do to recover that information. Now, we can also ask whether we can test whether the radiation is pure. So imagine that we make a black hole and it emits radiation, and you collect the radiation from this black hole, and then you want to test whether it's pure or not. So one thing you can do is you can make two identical black holes and let them evaporate, and then there is a certain thing you can do which is called the swap test, which is a test that you can do to see whether the two states are in the same pure state or not. And it's a relatively easy by at least complexity standards. So it's if you have n qubits, you don't have to do more than a further n operations to check it. So it's polynomial in the entropy rather than exponential in the entropy. And now I won't describe exactly what the swap test is, but you can read out what it is in Wikipedia or some other reference. But that's, for example, a test you can do. And it is relatively hard because you have to collect all the information, but well, it is as easy as you can get in terms of quantum information theory, or as easy as you could get just from the expectations, to test whether any state is pure, even of a few qubits. This is the best thing you can do. Now, I mentioned these few things that you can do, but there are things that are even more complicated that in principle you can do, but they are expected to be much more complicated. So for example, you can let the black hole evaporate so that the entropy of the remaining black hole is less than half of the thermodynamic entropy of the initial black hole. So if you send an unknown message into the initial black hole, we expect to be able to recover it from Hawking radiation. A special case of that is what we mentioned here, that we should also be able to recover it in this case. And there is, I will try to explain why this is the case, why we can expect to recover it. So imagine the following situation. So we have the initial pure state that collapses into a black hole. I'm calling it 0, but this is some arbitrary pure state that collapses into a black hole. And then we send a message. And in order to keep track of the message is a useful technique to entangle it completely with a reference system. Okay, so we have a message completely entangled with a reference system. And now we try to, we evolve the black hole and we end up with some black hole at late times and then some radiation. And we'll be in the regime where the amount of radiation is much bigger than the entropy of the remaining black hole. And the main tool that one can use to analyze this type of question is the following. So imagine that you have a factorized Hilbert space to 2 tensor factors and it's such that the dimension of one is smaller than the dimension of the other factor. Then if you have a fairly generic pure state in H, then rho A is very nearly maximally mixed. And this is a result derived by Page, by Don Page. Okay, so just simply by the fact that the dimension of the Hilbert space in A is very small, you're just somehow not getting the full picture of what the state is. And for that reason, that density matrix is sort of maximally mixed. So it's just the identity. So you don't get any information of what the state is if you look at at less than half of the qubits of the system. Okay, so now let's go back to this and imagine that the A and B here, A will be the black hole plus the reference system, for example, and B the radiation. So we're going to assume that the dimension of the radiation, here it should say that the log of the dimension of the radiation should be bigger than the area of the black hole plus the entropy of the reference system. So the dimension of this Hilbert space is much bigger than the dimension of the black hole plus the reference. So now I would like to argue that the mutual information between the reference and the black hole is very small, but the mutual information between the radiation and the reference is actually very big. So that this reference is now entangled with the radiation. And so in principle, we should be able to disentangle somehow this information and figure out, purify. Well, I won't discuss. For the moment, we just want to argue that there are correlations between the reference and the radiation, so that this message is somehow, so that the reference originally was correlated with the message, and we're finding that the message somehow made it into the radiation because the references will be correlated with the radiation. So mutual information for two systems is defined as the entropy of the first system plus the entropy of the second system minus the entropy of the union of the two systems, okay? And it's a measure of the correlations that exist between the black hole and the reference. Both quantum and classical correlations could contribute to mutual information. But in this case, when we calculate this, we see that the black hole union the reference system is a subset that is much less than the one, it has a dimension much less than the dimension of the radiation. And so the state here will be nearly maximally mixed. And so the entropy of this system will roughly be the entropy of the black hole plus the reference. So the mutual information between the black hole and the reference would be close to 0. Okay. But more importantly, the mutual information between the radiation and the reference well, we can calculate it as, again, the entropy of the radiation minus the reference, plus the reference minus the entropy of the union. So that's the general definition of the mutual information. And now here, when we look at the entropy of radiation, because the total space initially, the total state initially was pure, that entropy of radiation is the same as the entropy of the black hole plus the reference. But that we already seen that it was the entropy of the black hole plus the entropy of the reference. I should go to presentation more. Similarly here, the entropy of radiation union the reference, because again, it was a pure state, was equal to the entropy of the black hole. And therefore the mutual information will be twice the entropy of the reference. So it's nearly maximal mutual information. So we conclude that the entropy should be contained in the radiation, but it turns out that it is exponentially difficult to extract it. So there is an argument that was originally presented by Harlow and Hayden, and then this other paper made several other comments on this. And the conclusion is that in this case, it is actually exponentially difficult to extract it. So the difficulty is much more than the difficulty of evolving backwards in time. And this paper also made it clear that complexity is likely relevant for black hole discussions. So notice that the forwards in time evolution of the coupled system is relatively easy, because we are usually assuming, and it's true in ADS-CFT, for example, that the evolution of the black hole is easy to simulate, and it's easy to simulate in a quantum computer. And in some sense, if nature does it, it must be easy, must be somewhat easy to do. So there is this hypothesis that nature can only do the things that are not infinitely complex. But if we ask a question like the question we were asking before, like extract the qubits entangled with the reference system, that is actually exponentially difficult. Now that there is actually, I won't discuss it during these lectures, but if you're curious, you can go and check it. There is a certain so-called Python-Slange conjecture, which is a statement about precisely which operations in gravity are supposed to be very complex. And it has to do with the existence of certain surfaces that I'm going to discuss. Well, I'm going to discuss them in different contexts now. So we're going now to discuss a very important tool for the recent developments. I think probably Tom Harman will discuss this a little more, but I think since it's so important, maybe you'll hear it twice. And this is a formula for the fine-grained gravitational entropy of a system. So first, we need to distinguish two notions of entropy. So one is the fine-grained or von Neumann entropy, or sometimes called quantum entropy. Sometimes it's also called entanglement entropy. It's defined, so if you have some rho is the density of states, so if rho is the density matrix of the system, then you just take trace of rho log rho, and this by definition is this fine-grained entropy we're talking about. So it's somewhat analogous to the Shannon entropy for classical systems. And this entropy remains constant under unitary time evolution, because if you conjugate by a unitary here, you get the same answer. On the other hand, there is another entropy that we normally use in physics, which is the thermodynamic entropy, sometimes also called Boltzmann entropy. And it somehow arises from sloppiness. So it arises because we don't look at the whole system. We only look at the system of simple observables. And then if we have some state rho, we define some other state rho hat, which is such that for all simple observables, rho and rho hat give the same answer. But the entropy is just the maximal entropy of all rho hats, so that they agree with the so that they agree well, with the density rho, with the density matrix rho on the simple observables. So I mean, this observables A could be the total energy, the total charge, the volume, etc. And this notion of entropy depends on exactly which A's you choose. but this one could start increasing because some observables which at early times were simple then become complicated, and you might lose observables to look at. Okay, now we'll talk about this entropy, but I mentioned this one because this entropy, this type of entropy is the area of the horizon. So the Bekenstein-Hawking entropy is, which is the area of the horizon, is an entropy in this sense. So it's an entropy which under unitary evolution can increase, okay? For example, during the formation of a black hole, that's even before Hawking radiation is emitted, that's supposed to be a unitary process, but nevertheless, the area of the horizon increases, okay? So that's a Boltzmann-like entropy. But the entropy we're going to be concentrated now on will be this fine-grained entropy. And it turns out there is also a gravitational formula for the fine-grained entropy. And it was developed by various people. And the final formula is something like the following. So we look at the area of some surface, and we add the entropy of the semi-classical fields outside the surface, so similar to that formula for the generalized entropy we discussed before. But the difference is that instead of taking X to be the area, the horizon, we take X to be an arbitrary surface, and we extremize over the position of X. So let's say we have, this is a Penrose diagram. What happened? This is a Penrose diagram showing again the collapsing and evaporating black hole. And this blue line or purple line here, it's purple, I guess. It's some cutoff surface outside the black hole. And we're trying to compute the entropy at some time t. So what we do is we consider a space-like slice and up to some position x. And then we calculate the area of this X. So this is a point here because there is a two-sphere at each point on this diagram. So it looks like a point here, but it's really a two-dimensional surface. And we calculate the area of X plus the entropy of the quantum fields on this green slice. Very good. So we sum these two, and then we move this X, we move it inwards, or we move it up and down in time. Always keeping this surface space-like, and we find an extremum, so a point where if we move it up or down, this sum does not change. And if there are many extrema, then we minimize over all possible extrema. So that's the final prescription. And a surface that minimizes this, it's called the minimal quantum extremal surface. And the important point is that we are allowed to take the surface to the inside. So it's not the horizon area, it might be something else that is inside, and in general it might be smaller than the area of the horizon. And something very important is that it depends on the actual geometry of the interior. Okay, so for different interior geometries, you might get different fine-grained entropies. And so different interior geometries seem to be related, therefore, to different states the black hole can be in. And for different states, you'll get different answers. Now, there is this concept of entanglement wedge, which is, suppose you found this quantum extremal surface, minimal quantum extremal surface, and then you had the spatial slice. So then you look at the domain of dependence on this slice. So that means all the points in your space-time that you can get from initial data on this slice. So it's typically a wedge-like region like this. And so this is the so-called entanglement wedge. Maybe it should be called like the entropy wedge or the fine-grained entropy wedge, but for historical reasons, it was called entanglement wedge. Okay, and its importance is in the following hypothesis, which says that the quantum system that describes the black hole is supposed to describe everything that is included in its entanglement wedge. Okay, let me go back to the previous picture. So in this particular case where the point X was, let's say here, then the black hole does not, the quantum system that describes the black hole from the outside, so the quantum system that was appearing in the central dogma, does not describe the whole black hole interior. It only describes this wedge-like region. doesn't go all the way to the center. On the other hand, if this surface was all the way here, then it would describe all the way to the interior. So it depends on exactly what the geometry and the properties of the interior are. And you'll see examples in Tom Hartman's lectures. Now, by the word describe, what we really mean is that we can recover the state of a probe qubit inside this entanglement wedge. So if we have some probe qubit, that some message that someone sends, we can recover it. And the recovery is state dependent, so it depends on the state we have. And it's somewhat similar to quantum error correction. So Tom Hartman will discuss this, I think, in more detail in his lectures. But I wanted to emphasize that the key difference with previous ideas on black holes, for example, the idea of complementarity. The key difference is that we are not describing the full interior, but just a portion of the interior. Okay. Now, let me say a few words about the IDS-CFT or BFSS matrix model. So in both cases, in principle, these conjectures allow us to describe any computation that we can imagine for a black hole, any computation that we can formulate far away. So if we imagine that we have anti-de Sitter space, and that anti-de Sitter space is described by a theory that lives on the boundary, then you have some observable here. You can translate that into some observable in the boundary theory, and you can do any computation using the boundary theory. So, for example, you can imagine sending waves into the black hole and watching how those waves come out. So those are things you can do. But something we don't know how, well, something we are learning somehow how to do is how to describe an observable in the interior. So that we don't know how to do in general. For example, what the singularity means, that's not clear. And something we've seen just right now in the previous transparency is that we sometimes cannot describe the whole interior. Sometimes we can describe only a portion of the interior. Now I'd like to make now, well, maybe I pause for questions, perhaps. I should have paused before.
Yeah, so there are a couple of questions. So one is there in the chat box. I'll read it out.
Okay, let me look at it.
Yeah, this is by Takato. Doesn't the backward time evolution? Yeah. Yeah,
doesn't the backward time evolution need to act both on the radiation and its partner? Then even if you collect, yeah. Yeah, so the idea here is that you basically act only on the radiation. So that by acting on the radiation, you can recover the initial state. Of course, if you do the backward time evolution in the full bulk, then you need to act both on the radiation and the partner, as you correctly say here. But in principle, the idea is that just in the acting from the outside system, you should recover the initial radiation, the initial message. Yeah. Then there was another question here. Why? Well, that was a question about the previous transparency. Let's see. I was asked why this is equal to, let me see, S ref plus radiation. Yeah, so I said that the radiation plus the reference should be equal to the black hole entropy by purity. Okay, any other question?
Yeah, so there is a raised hand. Gopal, you can ask your question.
Yeah, can we choose this surface sigma x right to the extremal point, or we can just choose left to the extremal point?
The surface x.
Sigma x in the Penrose.
What do you mean by extremal point?
Yeah, this extremal point, capital X.
Yeah, X. Yeah, so X can be anywhere. So it can go all the way here to the center of the black hole. It can go in principle all the way here to the boundary. So it can be anywhere, and it can go up and down as long as it's space like separated from this point T.
Okay, the surface that you have drawn, sigma X, can we choose the surface right to the point X?
Right through?
Right to the point X.
Yeah, this surface goes from T to X. So X will move here, and this green surface moves together with X. So the green surface is goes from the boundary or the cutoff surface to that extremal surface X.
Okay. What will be the case when we have a mixed state?
Yeah, so for example, in this particular case, with that, if it goes up to here, the state will be mixed.
Okay.
So if this surface goes all the way to the center of the black hole, then it will have zero area. So we will not have a contribution to the entropy from the area. And then if the quantum fields here are in a somewhat pure state, then we'll have a pure state. So the entropy will be zero.
Okay, thanks.
Yeah.
There's a couple of questions.
Yeah, maybe at this point I would like to mention something related to this question. So imagine that we're doing this calculation just after the black hole collapses, right? Then if we calculate the entropy, the Hawking-Bekenstein entropy, it will be very large. It will be the area of the horizon. But if we calculate it using this formula, we will find that the one that minimizes this whole thing is when you take this point and you take it all the way to the center here, right? And then the area term will vanish, and the entropy of this piece will be just the entropy of the fields on this slice, and that will be just essentially the entropy of the star, okay? So if we calculate the fine-grained entropy after the black hole forms, it will give us the entropy of the star. So it's consistent with unitarity, it's consistent with unitary evolution.
Okay,
We
so
get
the
an
first
answer.
couple of questions. Yeah.
Yeah.
Yeah, so a couple of questions in the chat box. So what determines the size of the entanglement wedge?
Well, how big it is depends on the state of the fields, so and on the geometry. So because it depends on the area and depends both on the area and this semi-classical entropy. So it will depend. So it depends on the particular setup.
Yeah.
Yeah, so here there is the question of, are the entanglement wedge and quantum extremal surfaces defined in ADS, or can they be used for asymptotically flat space and so on? Well, it's true that the concept is more sharply defined in ADS, but for what we are using it here, we could define it in an asymptotically flat space, and we can define a cutoff surface. As long as the area of this cutoff surface remains constant, I think we can define this concept, and it gives some nice answers. We don't know whether we can be completely sharply defined in that case. So I mean, part of the question is when can we? Well, when do we expect that it is completely well defined, and when it isn't? For many purposes, we can do it, put in an arbitrary surface, but we don't know the precise limitations. So for an asymptotically flat space, it's also somewhat natural to take this point to be here on the boundary and to consider the entropy of radiation that crosses up to some point here on the boundary. Tom might talk about that. Is the black hole treated as a time-dependent classical object during the whole radiation evaporation process? And yeah, so the answer is essentially yes. So there is a classical black hole geometry that includes the back reaction due to the evaporation. Yeah, but then there the quantum, so the quantumness of the evaporation is in the quantum fields. So the statistics of quantum fields and so on that are evaporating. So that aspect is quantum mechanical. Any other question? Okay, well, then I'll continue. So I guess I will end with some simple remarks on the entropy. So it's important to, or part of the problem is that we do not know how to describe the black hole microstates. The black hole microstate, what I mean are the states of the quantum system that describes the black hole as seen from the outside. how do we describe them from the gravity point of view? So I'll now describe a very simple idea together with its limitations. So, and this comes from looking at the entropy of the quantum fields around the horizon. So the quantum state is highly entangled at short distances. And when we look at the fields outside the horizon, we find them in a thermal state. And so we can compute their entropy. And when we do that, we find that this entropy is UV divergent. So let me just show you this calculation. So we start with the entropy, with the metric of a black hole, of just the Schwarzschild black hole, for example. And we are going to look very close to the horizon where this factor is very small. So we're going to call it x squared. And if we do that, then we can pull out a factor of f here and define this metric. And this metric will have this geometry. So the geometry of, let's say, the time direction times this other factor will look a bit like hyperbolic space. Okay. Now this is sometimes called the optical metric. It's a metric you can use to look at the trajectories of light rays, because light rays don't care about these factors. Also, if you're looking at the entropy of fields at short distances, we can ignore the mass, and so it's essentially like having a conformal field theory. And for a conformal field theory, you can pull out any factor here, and then you can look at this system. And the advantage of doing this is that now you have a constant proper temperature. Okay, so the factor here is constant. And then you get some infinite metric, some infinite space, because x can go all the way to 0. And when x goes to 0, that looks like the boundary of this hyperbolic space. And so you have the divergence in the entropy coming from this. So you have a constant entropy density multiplied by this volume, which you get infinity. And so the entropy is just basically the area of this sphere times the volume of well, some factors that essentially come from the factor of the volume of this hyperbolic space. And it diverges x very close to 0, like 1 over x cutoff. So you cut off at some position. Now, of course, you can just do the same calculation by taking the integral over the volume of the original space times the entropy at the proper temperature of that entropy density at the proper temperature that you have at position r. And the proper temperature diverges, and for that reason, this integral will also diverge. So perhaps more pictorially, we can think of this calculation as saying that, well, if you have some unit cell, some distance from the horizon, and then you get close, so let's say this is has some size of order the temperature, and then as you get closer to the horizon, you have fluctuations over a size which is smaller, right? The temperature is higher, proper temperature is higher, so the size of a thermal wavelength is smaller. And as you get closer to the horizon, they get smaller and smaller. So you have this kind of fractal structure of basically, if you now blow up, so this is very similar to the diagrams of, again, hyperbolic space, where when you get close to the boundary, you have figures which have smaller proper size. So we should think of each of these cells contributing an order 1 amount to the entropy. Okay. Okay, so we got some entropy that diverges like area over epsilon squared, where epsilon is short distance cutoff. And this looks very similar to area over 4L Planck squared. So if we could choose epsilon to be 2L Planck, then we would be done and we would explain the entropy. The problem is that semi-classical gravity is valid. So the framework in which we did the calculation, it's valid when we choose epsilon much bigger than L Planck. Okay. Remember this whole story that we said about the counter terms and so on. So for that, we needed to be able to go order by order in perturbation theory, and that requires all these cutoffs to be larger than L Planck. So in fact, we can view this term as divergence, as the typical divergences that arise in effective field theory, and it can be absorbed into a counter term as a renormalization of G Newton. So we should really think of this as a correction to the entropy, and this 1 over epsilon squared is a renormalization of 1 over L Planck squared. So the conservative statement is really that this is a correction to the area formula, and it cannot be pushed all the way to epsilon equal 12 Planck within the validity of semi-classical gravity. Now, we could wonder whether a calculation like this could work if we did a computation in a UV finite theory, such as string theory. So then in that case, you might think perhaps the entropy could come from a gas of strings with ends at the horizon. So this was speculated by Sasken and Uglum, that perhaps the entropy comes from strings that end at the horizon. This is just, there is no, I would say there is no precise computation that makes this work. Okay, so well, I think we are done with time, right? So maybe we'll continue with this next time and perhaps finish with questions.
Okay, thanks Juan for a very, very nice talk. There is a raised hand. Gopal, you have a question? You can unmute yourself.
Yeah, I have one question on the generalized entropy formula.
Yes.
Maybe you can go to that slide.
There we go back.
Yeah. So in your 2013 paper, this semi-classical contribution to the entropy is order as part 0 correction to this entropy, right? First. So in Engelhard wall prescription, so they said that this entropy formula includes all corrections in H bar, higher order corrections in H bar. So in your paper, we can see that first term is order H bar inverse correction, and second term is order H bar 0 term. So how we can see that this formula includes all quantum corrections in this Engelhard wall prescription in terms of expansion?
I don't think it's correct to say that it includes all quantum corrections. I think there could be other corrections to this formula at higher orders in H bar. I think this is the correct formula, sort of in this semi-classical approximation. So the point is that this term, when we wrote this paper, we thought that this term would always be a small correction to the area term. Then if you assume maybe it's not a small correction, then it can compete in certain cases with the area term. And basically the main application, the main case where this can compete with an area term is for a black hole, for a situation like this, as shown by Pennington and Altmary et al. So I think Tom might discuss this in his talk. So the calculation of the page curve. So that's an application of, well, that's the sort of golden application of this formula in a situation where the semi-classical term can compete with the area term. So it can compete in this case because the area term is varying somewhat slowly near the horizon. So remember, the area is constant on the horizon. So along this direction, it's not varying very much. And along that direction, okay, it's varying somewhat. And the semi-classical piece is, well, it's also varying somewhat roughly in one of these directions. And that's why you can find the solution. You can balance the quantum effect against the classical solution.
Yeah, so I got confused that we cannot see this expansion in H bar. So in your formula, we can see that this first term is order H bar inverse term and second term is order H bar 0 term. So in this 2014 paper by Engelhard and Wall, we cannot see like we have order H bar inverse term, order H bar 0 term, order H bar term, order H bar square term, something like that.
Well, I think perhaps the way you can see it is the following: that this is formally a term that is of order H bar to the 0, but its effects can somehow accumulate and somehow produce a certain back reaction onto the geometry. But here there is no geometry; it's just this area term. So in some cases you can produce this back reaction, and that's what's included in the formula. It is conceptually similar to solving Einstein's equations with a stress tensor that is given by the expectation value of the T mu nu with the quantum fields on that geometry, right?
Okay.
I think in principle, there are higher order corrections to this formula. It's just that it's believed that those higher order corrections are not important.
Okay.
Imagine the following situation. Imagine you have a universe filled out of quantum radiation of photons, right?
Okay.
So that is a small quantum effect, just the thermal radiation of photons.
Yeah.
But if you have a very big universe, it back reacts on the evolution, and now you have to solve the Friedman equations with that source, right? Which is the source of the radiation of photons.
Yeah.
And that's in fact what happened with our universe. Well, in the far past, it was dominated by radiation, and you had to solve the equations in that way. So you can view that as an example of a situation where you have some quantum effect and well, reacting onto the classical geometry of space-time.
Okay, thank you very much.
Yeah.
Tushar, please unmute yourself and ask your question.
So I had two questions. So the first is, based on central dogma, what can the asymptotic observers say about the spectrum of the black hole? Like, can they, I think they can, well, just say that, okay, it's discrete, but can they say something about more finer properties of the black hole spectrum?
Yes, so that's an interesting question. So the first one is just in order to define the spectrum of the black hole, you have to be in a situation like ADS, right, where the black hole is really stable and does not evaporate.
Yes, I see.
Otherwise, it would be some kind of resonance, and it has a finite lifetime, so there won't be very well-defined states. But even in that case, we'll discuss perhaps in the third lecture what other things we can say about the spectrum.
Okay.
So there is an interesting calculation that talks about the correlations between energy levels, for example.
Yeah. Okay.
That we'll probably discuss in the third lecture.
Okay. Yeah.
But of course, the zeroth order statement is that the entropy formula gives us a kind of density of states, so you can translate between. Well, yeah. Essentially, the area tells us how many states you have for a given mass.
Yeah.
So, and that same formula tells us that the spacing between energy levels should be very small. It should be of order e to the minus s. Right?
Yeah, and okay.
These are just things that follow from the entropy formula.
Like, yeah, okay, the second question was related to that sort of, because entropy, the way that we define entropy as in one Neumann entropy, that's a non-linear quantity in rho. And usually we define quantum observables as being linear. So suppose we work with Rene entropy, then in that case, we construct multiple copies of the system to compute our the Rene entropy. But is there any like physical probe that a single observer moving along their own geodesic can use as a probe of information paradox, like some 2-point time correlation function of some background field or something? What is like a single probe that a single observer can use?
Yeah. It's true that entropy is not standard observable, and it's however, entropy has nice features, and it's interesting. What's perhaps the reason that entropy has been studied so much is that it has this very interesting formula, right, that we are seeing here, that is very geometrical and very geometric. So the entropy is directly related to the geometry of your space-time. And so that's why there was so much focus on entropy, I think. And yeah, also the fact that, entropy has the curious feature that this formula has the curious feature that it it gives you the actual entropy of the state, the fine-grained entropy, but using only the semi-classical geometry, which is supposed to be an approximation to the state. And so this formula is interesting also for that reason. You might see a little more if Tom discusses the page curve calculation. And we discussed this a little more in a review that we wrote with Almeri, Tom Harman, Tashdini, and Shaq William. You can have a look there. More discussion on the page curve calculation.
Okay, so there's a question in the chat box. Is the entropy of quantum fields around the horizon some avatar of the brick wall model? Then we may use the firewall transformation.
Yeah. This is essentially, I think, this calculation was discussed by Toft, so the idea is that the brick wall is just the cutoff, so you have some cutoff, and so this gives you the entropy. But sometimes also called the stretch horizon, so there's different names, but now you mentioned some kind of firewall transformation. I don't know what that is, so I don't think there is anything well defined that you can say about that. Well, I guess there's the speculation that somehow the whole interior comes from thinking about these modes in some way, but that's maybe that's just some speculation.
Okay, so I don't see any further questions. So let's thank Juan for a very nice first lecture. So we will have the second lecture by Juan again, same time tomorrow, and we will reconvene today at 7:30 p.m. IST for Damson's lecture. Thank you very much, Juan.
Okay, thank you very much, and best wishes to everybody. Yeah, bye-bye. I'll be looking at the Slack, so if you have some more questions, you can put them in Slack.
Okay, thanks.
All right.